Welcome viewers, in this video we will see the transformer equivalent resistance. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive, link is given in the description box. Now we will go to the topic equivalent resistance. Consider this transformer. This is the iron core having the primary winding and secondary winding. This winding is inductance coil, but this inductor also having some amount of resistance, that is called R1. This R2 is the resistance in the secondary coil. R1 is the resistance in the primary coil. Both primary and secondary coil is a inductive coil, but inductive coil also having some amount of resistance, that is called R1 and R2. Suppose we can transfer this secondary resistance R2 into primary, similarly primary resistance into secondary. At the time we need to find what is the equivalent resistance. When the resistance are transferred from secondary to primary or primary to secondary, there is a equivalent resistance equation is available. That equation we will see in this topic. So the R1 is the resistance of primary winding, R2 is the resistance of secondary winding. When all parameters are one side, calculation is simple. If you transfer all the parameter in one side, either primary side or secondary side, the further calculation will be simpler. So that we are transferring the parameters. Not only resistor, we can transfer resistor, current, voltage, everything we can transfer from one side into other side. Let us transfer the resistance. In this we will see the resistance of secondary winding R2 to the primary side. So we are going to transfer this R2 from secondary side to primary side. At that time, what is the equivalent resistance that we are going to obtain in this topic? So R2 dash is the equivalent secondary resistance after transferring to primary. So R2 is the resistor available in the secondary winding, while transferring into primary it become R2 dash. So R2 dash is nothing but equivalent secondary resistance referred to the primary. But R2 should produce the same effect in the primary as R2 produced in the secondary. So while transferring the resistance from secondary to primary, it have the same effect. The effect should not change. What is the effect available in the secondary by R2? The same effect should be produced in the primary with R2 dash. So that is our aim. For that we need to find the equivalent resistance, equivalent equation. If I1 is the current in the primary, I2 is the current in the secondary. We will consider I1 is the current flowing through the primary winding, I2 is the current flowing through the secondary winding. So drop across R2 in secondary is R2 is I2 square into R2. In the secondary side, the voltage drop across the R2 is I2 square into R2, because referring the secondary winding. The same thing in the primary winding. The drop across R2 in primary is nothing but I1 square, because now it is primary winding. Similarly, while referring the primary, the R2 is referred as R2 dash. So this is the normal one. I2 square R2 is the resistor available in the secondary and secondary current. While transferring primary, it become I1 square. Primary current is I1 square. The resistor become R2 dash. So based on that, these two are both are equal. Both the effects are equal. So I2 square equal to I1 square into R2. This is referring the secondary, this is transferred to the primary. So from this equation we can write R2 dash, this R2 dash equal to, bring this I1 square in the denominator. So I2 square divided by I1 square into R2, right. So this I2 dash is brought in the denominator, so that we can able to find the R2 dash. So that can be written as I2 by I1 the whole square. Here also square available, here also square available. So R2 dash equal to I2 by I1 the whole square into R2. We know that I1 by I2 is the K, transformation ratio I1 by I2. Here I2 by I1 is available, so that 1 by K, right, based on the transformation ratio I1 by I2 is K. So that I2 by I1 is 1 by K square. So R2 square R2 dash equal to R2 divided by K square. So R2 is the resistor referred in the secondary, while transferring to the primary it become R2 dash. So that equivalent resistance is R2 divided by K square. So when the R2 is divided by K square, we can obtain the resistor referring the primary. R2 dash equal to R2 divided by K square. So in general, if any parameter transfer from secondary to primary, normally it is divided by K. While transferring from primary to secondary, it is multiplied by K. Now we'll go to the total resistance. So the total resistance in the primary is the R01. By referring primary as well as secondary, it is nothing but R1 plus R2 dash. R1 is the resistor of the primary, R2 dash is the secondary resistor, while transferring to the primary it become R2 dash. So R1 plus R2 dash is total is nothing but R01, that is equivalent resistance of the transformer as referred to the primary. That is the secondary resistor is transferred to the primary, so that it is called R01. See the refer the diagram. R1, this is the primary winding resistance. R2 dash is the secondary winding resistance transferred to the primary. So both are connected in series, so it is added together. That is nothing but R01. So R01 equal to R1 plus R2 dash. So now the resistor is transferred to the primary, so the any calculation it will be easier. Only we have R01, that is equal to R1 plus R2 dash. So that it is transferred. Similarly, if the resistor is transferred from primary to secondary, next one we will see the when the resistor is transferred from primary to secondary winding. What will happen? The resistance in the primary is R1. When it is transferred to secondary, it is denoted as R1 dash. Right? R1 is the original resistor available in primary, while transferring to secondary it become R1 dash. Now what is the drop across R1 in primary? I1 square into R1. Primary means I1, the resistor also R1. But what is the drop in secondary? While going to the secondary winding, automatically it will become R2 square and I2 square into R1 dash, because while transferring secondary it become R1 dash. So I1 square, R1 means primary side, while referring secondary I2 square into R1 dash. So based on that, is both the effects are equal. So while transferring any parameter, we need to maintain the resultant effect should be equal. There should not be any deviation. That means these two drops are equal. So I1 square R1 equal to I2 square into R1 dash. So that I1 dash, this I1 dash, bring this I2 dash in the denominator. So that I1 square divided by I2 square into R1. So that can be written as I1 by I2 the whole square. I1 by I2 the whole square. We know that I1 by I2 is K. In the previous case we have I2 by I1, so that we put 1 by K, but I1 by I2 is the K transformation, so directly we can put. So R1 dash equal to K square into R1. So this is the resistor transfer from primary to secondary. So it is multiplied by K square. Previous case divided by K square. So that we can refer that the total resistor in the secondary side is R2 already available, while transferring the primary it is R1 dash. So that can be written as R02, equivalent resistance of the transformer as referred to the secondary. This is R02. So see this diagram. The primary winding and secondary winding, the primary resistor now transferred to the secondary, so it become R1 dash. Both are in series, so that can be written as R02. So that R02 equal to R2 plus R1 dash. Now we can make the calculation because only we have the parameter in the secondary. So we discuss that resistor transfer from secondary to primary as well as primary to secondary. Similarly, we can see the leakage reactance. All the flux does not flow in the core, some amount of flux flowing through the air, both in primary and secondary winding. The leakage flux give EMF in the primary and secondary winding. It is shown by reactance connected to the primary and secondary winding. So the reactance will be available. Due to that, the flux is not flowing in the core, so that EMF is produced. So that is denoted as a reactance. X1 is the reactance in the primary, X2 is the reactance in the secondary. So similar to resistance, we can transfer the reactance also from primary to secondary as well as secondary to primary. All the reactants can be transferred to any one side, right? Now consider this X2 dash, that is reactance of secondary winding transferred to the primary, X2 dash, right? Now the secondary, from secondary winding reactance is transferred to the primary, so that X2 dash. But X2 dash would produce the same effect in primary as X2 in the secondary, like previous resistance also same thing we discussed. Here also this X2 dash effect should be same as X2 in the secondary. So each must be having the same reactive power. What is the reactive power? Is nothing but VAR, that is VI sin pi, that is nothing but I2 into X, current into reactance, I2 into X. So equating the VA consumed by X2 dash and X2 is nothing but I1 square X2 dash equal to I2 square into X2. So this is the original one, secondary, I2 square X2. While transferring to primary, it become I1 square. The reactance become X2 dash, right? X2 become X2 dash. Current is from I2 to I1. So from that we can find X2 dash equal to, bring this I1 in the denominator, I2 square by I1 square into X2. We know that I1 by I2 is K, here I2 by I1 is available, so it is minus 1 by K, it is equal to 1 by K. So what is the final thing? X2 dash equal to X2 divided by K square. Similar, very similar to resistor, right? So while transferring to primary, we have X2 by K square. So what about the total reactance? X2 dash is the equivalent secondary reactance referred to the primary. So the total reactance in the primary is X1 as it is in the primary. So from secondary is transferred to primary, it become X2 dash. So X01 total reactance is nothing but, in the primary is nothing but X1 plus X2 dash, the equivalent reactance of the transformer as referred to the primary. The reactance is now transferred to primary. Similarly, if it is transferred from primary to secondary, what will happen? X1 dash equal to K square into X1. Here X square divided by K square, here K square into X1. Normally when the parameter transfer from primary to secondary, it is multiplied by K square, secondary to primary divided by K square. So that the total reactance is in the secondary X02 equal to X2 plus X1 dash. Here available X1 plus X2 dash, similarly here X2 plus X1 dash. Similarly we can refer the current and voltage also. I2 dash equal to K into I2. I1 dash equal to I1 by K. Similarly V2 dash equal to V2 by K. V1 dash equal to K into V1. We already discussed the primary means multiplied by K, secondary means divided by K, but in current it is reverse, right? The primary means divided by K, secondary means multiplied by K. Only the current, because the transformation they say we know that V2 by V1 equal to N2 by N1, but current is I1 by I2. While increasing the voltage, the current decreases, so that I1 by I2. So this here also we referred. So accordingly, this law of this procedure applied, this K multiplied by K primary divided by K secondary is applicable, but while going to current it is reverse. So in this video we discuss the equivalent resistance as well as reactance while transferring from primary side to secondary. What is the equivalent resistance? What is the expression for both resistance and reactance? Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Welcome viewers, in this video we will see the equivalent circuit of transformer. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we will go to the topic, equivalent circuit of transformer. So that we know that the transformer we have primary winding and secondary winding. This is the primary winding. This one secondary winding. The primary winding is applied with the voltage. Secondary winding is connected with the load. So V1. V1 is the voltage applied to the primary winding. V2 is the voltage available at the secondary terminal as a load voltage. E1 is the EMF induced in the primary winding. E2 is the EMF induced in the secondary winding. R1 is resistance of primary winding, X1 is reactance of the primary winding. R2 is resistance of secondary winding, X2 is the reactance of secondary winding. We have the no load condition and loaded condition. When the transformer is not loaded means the secondary is not connected with any load. At that time, the small amount of current I0 will flowing through the primary winding. This I0 is the no load current, that is when the secondary is not loaded, small amount of current flowing, that is called I0. This I0 having two components, working component and magnetizing component. Working component means it is equivalent to the resistance, that is the iron loss. Working component means it is responsible for producing the magnetic flux. It is like a inductance, reactance X0. Right. So the IW is the current flowing through R0, that is called a active or iron loss component. This I mu is the magnetizing current flowing through the X0. This X0 R0 refers the no load condition. It is responsible for magnetizing the primary winding when it is the secondary is not loaded. When the secondary is loaded, what will happen? The secondary current will flowing through the secondary winding, so that the current also flowing through the primary winding. It's called I2 dash. I2 is the current flowing through the secondary winding when it is loaded. So due to that, because of loaded condition, some more current will flow through the primary, that is called I2 dash. So this I1 is the total primary current, that is the sum of I0 and I2 dash. I0 due to no load condition, I2 dash due to loaded condition. So vector sum of these two is nothing but a total current I1. I2 is the current flowing through the secondary winding. Now we can transfer this all the parameters in the secondary winding to the primary winding, so that we can frame the equivalent circuit. For further calculation or the other process, it will be easier while transferring all the parameter from secondary to primary. Right. Now we will see the description here. So the V1 is the applied voltage in primary. V2 is the output voltage, terminal load voltage. I1 is the current in the primary. I2 is the current in the secondary. E1 is EMF induced in the primary. E2 EMF induced in the secondary. R0 and X0 be the resistance and reactance represent the loss component at the no load during no load condition. The effect of magnetizing component is X0. The effect of core loss, that is iron loss, is R0. So these are all the description available. Now let us transfer all the resistance and reactance to the primary side in order to frame the equivalent circuit. That will be very easy for further calculation. So we will transfer all the reactance available in the secondary to the primary side. What are the resistance available? In the secondary side we have EMF, induced EMF, secondary current, secondary resistance, secondary reactance, as well as load impedance ZL. Now we will transfer all these parameters 1, 2, 3, 4, 5 parameters into primary side. All these parameters are transferred to the primary side. So while transferring the primary side, we need to find the equivalent expression. We cannot transfer as it is. When R2 is available in the secondary while transferring to the primary, we need to find what is the equivalent expression, because the effect of R2 in the secondary should be same as in the primary. The effect should not change. The originality will not change. So while transferring to primary, we need to find what is the equivalent expression and what is the equivalent equation for that. So while transferring the resistance R2 to the primary, it's become R2 dash. R2 is the resistor available in the secondary, while transferring to primary automatically it become R2 dash. That is equivalent to R2 divided by K square. So this equivalent resistance available in separate video, link is given in the description box. Why we are divided by K square, the details are available. Normally while transfer to primary it is divided by K square, while transfer to the secondary it is multiplied by K square. The normal formula. Similarly, when X2 reactance is transferred to the primary, it becomes X2 dash, that is X2 divided by K square. Similarly, impedance, load impedance ZL transferred to the primary, it becomes ZL dash, that is Z1 ZL divided by K square. Similarly, the current, secondary current I2 transferred to the primary, it is I2 dash, K into I square. Only for current it is multiplied by K. We know that the transfer function K equal to N1, N2 by N1, V2 by V1, but current is I1 by I2. It is reverse. So that all these terms are divided by K square, but current only multiplied by K square. It is opposite to each other based on the transformation ratio. Similarly, E2 in the secondary, EMF induced in the secondary, while transferring to primary it become E2 dash, that is equal to E2 divided by K, that is nothing but E1, that is can be treated as E1. Both are in phase. Now all these secondary parameters R2, X2, ZL, I2, E2 are transferred to primary. At the time it become R2 dash, X2 dash, ZL dash, I2 dash and E2 dash or Z1. Now it is transferred to the primary. So based on that we can redraw the diagram, redraw the equivalent circuit. So this is the applied voltage, this current I R1, X1, this I naught, all are available in the primary side. Now the secondary parameters also transfer to the primary. So what will happen? Automatically it become R2 dash, X2 dash, E2 dash, V2 dash, ZL dash. So this equivalent expression also already we calculated. Now we have only one side, primary side. This is the primary side parameters. These are all secondary side parameters, equivalent secondary side parameters R2 dash, X2 dash. And this is the no load component. This is no load component I naught. Now we have only one side. So we can go for further simplification. The value of no load current I naught is very less compared to the I1. This is only due to no load condition, only negligible amount of current flow, that is for magnetizing the circuit at initially. So the effect of I naught can be neglected while compared to I1. While compared to I1, I naught is very less, so that we can neglect. So if you neglect this I naught, we can go for the equivalent circuit will be simplified, so that we can draw like this. This no load component is now neglected. So we have now don't have any no load component, only we have R1, X1 primary resistance and reactance, R2 dash, X2 dash secondary side resistance and reactance. So these are all connected in series, so that we can write R1 plus R2 dash equal to R01. X1 plus X2 dash can be written as X01, because both are connected in series. This one parallel circuit no load component we neglected. Now we will see what is the further simplification of this circuit. So that we can write it as R01, X01. This current also I1 equal to I2 dash. This V1 and ZL dash. This R01, X01, this resistance and reactance is nothing but impedance Z01, or modulus of Z01 equal to square root of R01 square plus R2 X01 square. So that we can write Z01. So finally we have only very simplified equivalent circuit. Applied voltage V1, then impedance, load impedance ZL dash, then Z01 referring primary as well as secondary impedance, total impedance of the transformer referring primary and secondary. Very simplified circuit. For finally we got the very simplified equivalent circuit. So in this video we discuss about the equivalent circuit of a transformer, that is all secondary side parameters are transferred to the primary. At that time the equivalent equation also we framed, based on that it is transferred, and finally we got with the very simplified equivalent circuit. Subscribe the channel for more videos and notification. The link is available, the soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers, in this video we will see the transformer test. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we will go to the topic. Transformer test. The performance of transformer can be calculated on basis of the equivalent circuit which contain the four main parameters. In order to draw the equivalent circuit, we need these four parameters for further analysis. One is equivalent resistance R01 or R02. This is R01 means referring primary side, R02 means secondary side. Equivalent reactance X01 and or X02. Core loss resistance R0, reactance X0. By using these four parameters we can go for a equivalent circuit. From the equivalent circuit we can analyze the performance of the transformer. In order to identify these four parameters we need to do the transformer test. There are two types of tests available: open circuit test or no load test, short circuit test or impedance test. So these above four parameters are calculated from these two tests performed on the transformer. No load test, that is open circuit test OC test, and short circuit test AC test. In this video we will see the open circuit test. The open circuit means the secondary of the transformer is kept open, that there is no load connected in the secondary side, that is called a open circuit. Let us consider this transformer. This is the primary winding, this one secondary winding, this is a low voltage winding. Always no load test is performed on the low voltage winding. High voltage winding is kept open. This is high voltage winding. All test is performed on low voltage winding in case of open circuit test. High voltage winding is kept open. So this is a single phase supply available, phase and neutral. It is connected through the DPST switch, and the variac is available in order to vary the input voltage given to the transformer. Variacs, nothing but a autotransformer. Here we have ammeter, wattmeter and voltmeter. This ammeter used to measure the current flowing through the primary, voltage across the primary voltmeter. Wattmeter will measure the input power. The output side one more voltmeter is connected. So the no load means secondary is kept open. Now the supply is given to the primary winding by closing the DPST switch. By varying this variac, the rated voltage is applied to the primary winding. The rated voltage is applied by adjusting this the variac. So now the rated voltage will be given to the primary. Secondary is kept open, so there is no current flow in the secondary, but only the no load current I0 will flow through the primary, because secondary is kept open, there is no possibility of any load current in the secondary. So due to that, current flowing in the primary also very less, that is called a no load current. So this ammeter will measure the no load current. This voltmeter will measure the primary rated voltage. Similarly, this wattmeter will measure the no load input power given to the primary. No load input power given to the primary. So ammeter read the no load current, voltmeter read the rated voltage, wattmeter read the no load power. Since there is no load available, the current flowing is very less, so we can neglect the copper loss. There is no copper loss because only negligible amount of current flowing through the winding. So the power given to the primary winding is refer only the iron loss. There is no copper loss. since the current is very less, there is no possibility of any copper loss. The loss due to only iron loss. So, the power read by this wattmeter will represent the iron loss of the transformer. So, because from this iron loss we can able to find the this no load reactance, that is the core loss resistance R naught and reactance X naught. Now, we will see the description one by one so that you are able to understand. So, I will explain again. The secondary circuit is kept open. The primary rated voltage is given to the primary winding by varying the variac. So, this ammeter will read the no load current, voltmeter read the rated voltage, wattmeter read the input power. Because of less current, the power is only the due to the iron loss. There is no copper loss. So, the wattmeter reading refer the power consumed by iron loss. Now, we will see the description. Open circuit test is performed on the low voltage side of the transformer. It is called as open circuit test because high voltage side is kept open. In this, we are going to find the R naught value, that is core loss resistance, reactance during the no load and core loss. To the LV side, a wattmeter is connected to measure the power consumed. Ammeter is connected to measure the current. Voltmeter is used to measure the voltage. Supply is given to the LV side. Rated primary voltage V1 is given to the primary side by varying the variac. Now, the secondary side is kept open, so only the no load current is flowing through the primary winding, which is read by the ammeter. The wattmeter read the power input, but at no load. So, no load power input equal to only losses, that is equal to iron loss plus copper loss. There is no load available. So, the power read by the wattmeter refer only the losses, iron loss and copper loss, but the no load current is very small. There is very small, and copper loss I naught square is very small and negligible. So, the power input refer only the iron loss. It refer only iron loss because current is very less. So, the copper loss also very less, that can be neglected. So, the wattmeter reads only the power, that is referring the iron loss. So, wattmeter refers only iron loss. Voltmeter refers the primary rated voltage. Now, we will see from that how we can calculate I naught and X naught. The voltmeter refers the primary voltage, rated primary voltage V1. Ammeters reads the no load current I naught. Wattmeter reads the iron loss W naught. So, the W naught can be given as V1 I naught cos pi naught. Cos pi naught is the angle between V1 and I naught. So, cos pi naught equal to W naught divided by V1 I naught. So, from that pi naught, the angle between, phase angle between V1 and I naught can be calculated as cos inverse W naught divided by V1 I naught. Now, we got the phase angle between current and voltage. From that, we can find the two parameters. Working component is nothing but a iron loss, I naught into cos pi naught. Similarly, magnetizing component I mu is I naught sin pi. And phasor diagram is available in the phasor circuit. From that, we can obtain this formula. Further, the separate video is available. So, working component, the I naught is having two components, working component and magnetizing component, that can be calculated from this formula. This pi naught is calculated here. Pi naught is calculated from this reading. This I naught already available, wattmeter reading. Now, we got IW and I mu. From that, we can find this resistance and reactance. Reactance X naught equal to V1 divided by I mu. Resistance R naught equal to V1 divided by IW. IW refers the working component and iron loss, that refers the resistance. Both are in phase. Reactance refers the magnetizing current responsible for magnetic flux, that is out of phase, 90 degree out of phase. So, reactance refers the magnetizing current. So, X naught equal to V1 by I mu, R naught equal to V1 by IW. So, in this we discuss about the open circuit test. Our final aim is to find the X naught and R naught, that is given by V1 by I mu, V1 by IW. This V1 is nothing but rated voltage read by the voltmeter. This IW and I mu calculated from these two formula. In this I naught is nothing but no load current read by the ammeter. This pi naught is calculated from this formula. Here we have W naught V1 I naught. W naught is nothing but power, the wattmeter reading. That is nothing but the power input to the primary winding. That refers only iron loss, because current is very less, we can neglect the copper loss, right. So from wattmeter reading, voltmeter reading, current ammeter reading, we calculated pi naught. From there we calculated IW and I mu. From there we calculated X naught and R naught. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers, in this video we will see the transformer short circuit test. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we will go to the topic, transformer short circuit test. So we have two different tests available, open circuit test and short circuit test. Open circuit test available in the different video, separate video, link is available in the description box. This open circuit test and short circuit test is used to find the four parameters: equivalent resistance, equivalent reactance, core loss resistance and reactance, that is R01, X01, R0 and X0. This R0 and X0 no load component is calculated from open circuit test. This equivalent resistance and reactance R01 and X01 is calculated from the short circuit test. So our aim is to find these four parameters in order to draw the equivalent circuit. From the equivalent circuit we can go for further analysis of the transformer. Now we will go to the topic. So we have the primary winding and secondary winding is available. This is the low voltage winding. The low voltage winding is short circuited. The test is performed on the high voltage winding. The short circuit test is performed on high voltage winding, and low voltage winding is short circuited. So we have the supply available, phase and neutral, single phase AC supply. It is connected through the DPST switch by the variac. In order to apply the rated voltage, we can vary the voltage by this variac. We have ammeter is available in order to measure the current, and wattmeter available, we can measure the input power, and voltmeter available, we can measure the voltage across the high voltage winding. Now the supply is given by closing the DPST switch. By varying this variac, we can apply the rated current. In open circuit test we applied the rated voltage, primary rated voltage. Now in order to measure the copper loss, we are applying the rated current. By seeing this ammeter, we need to refer the rated current is applied to the transformer. How to measure the rated current we will see by later. So by varying the variac, the rated current is applied to the primary winding. The secondary winding is short circuited. So the applied voltage is very less, but the current is more. The rated current is applied. So the loss happen in the winding is fully the copper loss, because the voltage is very less, the core loss can be neglected. Only we can consider the copper loss. So power measured by this wattmeter is nothing but copper loss reading of the copper loss value. So this ammeter will measure the rated current of the transformer. Voltage meter will measure the voltage across the high voltage winding. This wattmeter measure the input power, that refers only the copper loss, because current is more, so the copper loss also more. Voltage is less, so that we can neglect the iron loss. Now we will see the description so that we can go for more details. So the short circuit test is done on the high voltage side of the transformer. It is called short circuit because the low voltage winding is short circuited. So by using this we are going to measure copper loss R01 and X01 or Z01. R0 and X0 is calculated from open circuit test. So our aim is to find these two values as well as copper loss. So to conduct this test, LB side winding is short circuited. supply is given to the high voltage winding. So this ammeter, voltmeter and wattmeter are connected to measure the power, voltage and current. The supply is given to the high voltage side, increased until the primary rated current is flowing in the circuit. So because of short circuit test, we need to apply the vary the variac until the primary rated current, rated primary current. In case of open circuit test, we applied primary rated voltage. Now we need to apply primary rated current, rated primary current. How will you find the primary current? I1 equal to kVA rating of the transformer divided by V1, voltage of the primary winding. So kVA divided by V1, we can get the rated primary current. So by varying the variac, we need to apply rated primary current. Now the applied voltage is low, so the core loss is less, that can be neglected. At the same time, the current is more, so copper loss will be more. So the wattmeter reads only the value of copper loss. This iron loss is neglected. Total loss is iron loss plus copper loss. Because of low voltage, iron loss is neglected. Only we can consider the copper loss. So the wattmeter reading is nothing but the value of the copper loss. So therefore wattmeter reading equal to WSC, short circuit power copper loss, that is equal to copper loss. Copper loss is ISC square into R02. This ISC is the short circuit current and this R02 refers the secondary side. So R02 equal to WSC divided by ISC square. So our one aim is to find this R02. So this calculated from the wattmeter reading, the resistance of the transformer, equivalent resistance of the transformer is calculated from this wattmeter reading. R02 equal to WSC divided by ISC square. We assume that only we have copper loss, iron loss is neglected. So ammeter reading is nothing but a short circuit current, ISC, that is equal to I1, rated primary current. Voltmeter reading is nothing but voltage required to drive the rated full load current. This voltage equivalent to the full load current. What is the voltage while applying the full load current? So VSC. So this VSC equal to ISC into Z02. Short circuit current voltage equal to short circuit current into Z02. Impedance of the transformer. From that Z02 equal to VSC by ISC. So by rearranging we can get. So this impedance also now calculated. The reactance. So already we calculated the resistance and the impedance. From that we can calculate the reactance. X02. X02 equal to square root of Z02 square minus R02 square. So we calculated reactance also. So in this we have ammeter, voltmeter and wattmeter available. Wattmeter refers the copper loss. Input power given to the transformer, we assume that power is equivalent to the copper loss, because iron loss is neglected because of low voltage. Because of high current, we consider only copper loss. And wattmeter and ammeter reads the short circuit current, because we are applying the rated current. So equivalent to that rated current, the voltmeter reads the short circuit voltage, VSC. So from this VSC, ISC and WSC, we calculated R02. From wattmeter reading, we calculated R02. From this VSC and ISC, we calculated impedance. From impedance, the reactance is calculated. So by using this, we can draw the equivalent circuit. So further performance can be analyzed from the equivalent circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.